Welcome to Scholar Sauce. The last video that I posted on this channel was a series of math facts that sound fake but are actually true. And I promised in that video that I would follow it up with another video that went into more detail to explain why some of those math facts were true. So here we'll take a look at each of those facts in turn, and we'll try to give some explanation for why those facts end up being true. Some of these topics are a little more complicated than others, and so we won't go into as much detail into those ones. But the ones that are a little more accessible, I think, will be pretty fun. And hopefully you'll find something that you either didn't know before or might just enjoy the ride. So the first fact that we're going to look over is the fact that I to the I is a real number. Now, in order to understand this, we need to first look at something called Euler's formula. And this will actually help us with the second fact too. Euler's formula says that e to the I theta is equal to the cosine of theta plus I sine theta. Now, even this on its own requires a little bit of explanation. Why do we know that e to the I theta actually equals this? This actually comes down to something called the Taylor series. If we have some variable z here, e to the z can be written as an infinite sum of polynomial function as follows. This goes on forever. This series is absolutely convergent, and if you want to know more about it, you'll probably need to take a calculus class. Usually sequences and series are taught in the second course in calculus. But we have a few other Taylor series that are also important here. Let's write down what the cosine of theta would look like. It goes on forever. You'll notice that this is picking up, it looks similar to that, only it's picking up even powers, and it's alternating sign. The sine of theta is actually kind of similar to it. This has it almost looks the same as well. It has odd terms, and it also alternates sign, positive, negative, positive, positive, negative, positive. So they're both kind of doing that. Well, what happens if we put in e to the I theta into this equation up here? Well, you'll get 1 plus I theta over 1 factorial plus I theta squared over 2 factorial plus I theta cubed over 3 factorial plus I theta to the 4th over 4 factorial, and so on. Well, when we square I theta, you get I squared times theta squared. And I squared is just -1 because remember, I is equal to the square root of -1. Okay? So here, if we resolve this, we end up with 1 plus I theta over 1 factorial. I squared is -1, so that's minus theta squared over 2 factorial. I cubed will be I squared times I, so it'll be -1, which is I squared, times I, or negative I. So this will be minus I theta cubed over 3 factorial, plus, and then I to the 4th is I squared times I squared. I squared is -1. -1 times -1 is 1, and so it ends up getting back to 1, and you get theta to the 4th over 4 factorial, and so on. Well, this pattern just repeats in terms of the signs here. E to the I theta, then, what we'll do is we'll separate all the ones that don't have an I and the ones that do have an I and see what happens. So over here, the ones that don't have an I will give us 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial. The next term would be the theta 6 term, and it repeats with that kind of thing, so it's going to look like that. And then we'll have plus, now we pull the I out and we do all the I terms. And you get theta over 1 factorial minus theta cubed over 3 factorial plus ... So what you can see here is that this guy right here is precisely this first series, and that this one here is precisely this series. So this ends up becoming cosine of theta, and this ends up becoming sine of theta, and that's where we end up resolving it out. So those two things combine, and we get e to the I theta is equal to the cosine of theta plus I sine theta. And that's one way to derive Euler's formula and why it has to be true. So let's erase this here and put Euler's formula at the top and see how this helps us understand that I to the I is a real number. You can look real quickly at the fact that this is e to the I theta makes you wonder that what would happen if you took the natural log of it. Okay? Take the natural log of e to the I theta, and what you'd end up with is the natural log and the e should kind of cancel, and you should end up with I theta. Well, this theta here has some kind of angle that's going on with this. If we plot this guy here as a complex number, This is the real part. So that's what this axis is. This is the real axis, and then this is the imaginary axis. So out here we have cosine theta as like an x coordinate and sine theta as a y coordinate. Well, that's precisely what the unit circle does. The x coordinate on the unit circle is cosine theta, and sine theta is the y coordinate. So this is representing complex numbers e to the I theta as elements on the unit circle here. And this angle here is precisely the theta. The natural log of this guy here produces I times that angle. But there's a catch. If you were to go around the circle one time, you'd come back to another angle that also hits that there. And so if I had e to the I theta, whatever it is, it turns out that e to the I theta is the same number as e to the I theta plus 2 pi. Because if you just go around the circle once, which is the 2 pi, you end up getting back to the same exact place that you were. So if you take the natural log of this number here, do you get I times this theta, or do you get I times this guy? And you don't know. Because of that, the natural log on its own is not really a function here. So we have to pick a branch or pick a region around the circle that we're going to say that's where I want the angles to come from. The principal one that we do goes from negative pi to pi. So negative pi to pi. Any angle in between negative pi and pi is what we call the principal argument or the principal angle associated with a complex number, e to the I theta. And computing that, we use something called the principal natural log. The principal logarithm, we use a capital letter for that. So the capital natural log of e to the I theta, where theta is between negative pi and pi. Notice it's less than or equal to pi here because we're allowing this guy here, the -1 mark, to be associated with the pi angle rather than the negative pi angle. And that'll just produce I theta, which is sometimes written as the argument of e to the I theta with a capital A, which is just the theta if it's here. So this brings us to how do we handle I to the I? Well, one fact that we'll need here is what I is equal to in this format here. I is up here, which has an angle of pi halves associated with it. And sure enough, cosine of pi halves would be 0, sine of pi halves would be 1. And so if I put in pi halves for theta, I do indeed get I. And so this will be e to the I times pi halves. That's what I equals, is e to the I pi halves on this guy here. Well, let's see what happens then if we take the principal natural log of this guy here. The natural log of I to the I. Well, that's going to be equal to I times the natural log of I. But I, of course, is this guy here. I times the natural log, the principal natural log of e to the I pi halves. So this will equal this I here, and then the natural log of this piece here, which is equal to another I times the argument here. Well, the argument, the principal argument, is just the pi halves. That's in between negative pi and pi. So this is going to have a pi halves here. Sure enough, I times I is -1, and this just is equal to negative pi halves. So the natural log of I to the I, principal natural log of I to the I, is negative pi halves. Well, it's true that if I then take e to the natural log, the principal natural log of I to the I, that I'll just get I to the I. But this natural log here was just this negative pi halves, and this results in e to the negative pi halves equals I to the I. And that's why we know that that fact is indeed true. We can also use Euler's formula to help us with the next fact. This is actually quite a bit easier. E to the I theta, as we said before, is cosine theta plus I sine theta. Well, the second fact that we mentioned was Euler's identity, which is e to the I pi plus 1 equals 0, or e to the I pi equals -1. Well, that's just plugging pi into this. So e to the I pi is equal to the cosine of pi plus I sine of pi. The cosine of pi, of course, is all the way over here, so that's -1, and sine of pi is 0. So this is -1 plus 0i, or just -1. And of course, the Taoists prefer e to the I tau, which is equal to e to the I times 2 pi, which would be the cosine of 2 pi, or cosine of tau, whichever you prefer, plus I times the sine of 2 pi. 2 pi goes all the way around the circle, and so back to where it started. And so the cosine of 2 pi will be 1, and the sine of 2 pi will be 0. So this will give us 1 plus 0i, or just 1. And so that's where we get the two equations. E to the I pi is equal to -1, and e to the I tau is equal to 1. The next several facts had to do with really, really large numbers. There's not really any major explanation needed here. These are just simple arithmetic calculations. For example, the first number that I put up on the board was that 1,000 seconds is equal to about 17 minutes. Well, this is simply, the way you figure this out is you just convert seconds into minutes. So 1,000 seconds, I used kind of a cool trick I learned in chemistry to change units. 1 minute, that's what we want to convert it to, is in minutes. Well, a minute to seconds is 60 seconds. And this tells us to multiply across the top, divide across the bottom. And so the seconds will cancel, and you end up with 1,000 divided by 60, which, don't tell anybody, but I'm going to use my trusty calculator to try to figure this out. So 1,000 divided by 60 is about 16.67 minutes. We just changed the units. And I just rounded up to 17 minutes. Basically, all the computations we did were based off of just unit conversion between these kinds of things and figuring out sort of how many seconds there are. The really interesting fact when you get all through all this is the claim at the very end when I say that a googolplex is basically just as far away from infinity as 1 is. And that's kind of a curious thing, because if you count the numbers from 1 to infinity, you just write out the natural numbers and they just go on forever and you never run out. Well, if I start with a googolplex, which I'll abbreviate as just a GP, well, I could add 1 to that, and then I could add 2 to that, and 3, 4, and these guys line up. And in fact, every number that comes after a googolplex is associated with the number that's over here. And so I basically counted all the numbers after a googolplex with all the regular numbers. So there's just as many numbers here as there are numbers after a googolplex, and it didn't really matter. You can kind of think of it like this. This is sort of like taking your number line, right, which has a 0 here. It goes on for infinity that way. It goes on for infinity this way. And just shifting where you place your 0 over here at one googolplex. And just call that 0, and you get a new number line here. That's like that. Well, you still have an infinity that way, and you still have an infinity that way, so it doesn't really matter that you got that far. So no matter how big it is, it still has an infinite way to go. And that's actually kind of a much more interesting fact, I think, than just the idea that the googolplex is a remarkably large number. Incidentally, I actually threw out something that I was going to include in this video because it just got too complicated. If you're interested in seeing a number that just absolutely dwarfs the googolplex number here in such a way that like we had to invent notation even to describe how big this number is, try Googling Graham's number. It's kind of crazy. The next facts that we mentioned in the video had to do with geometry and topology. So the first one was the idea of a Mobius band. Well, if I take a strip of paper, the first thing I mentioned was that you could turn it into a cylinder by just rolling it up and gluing it on each side. That's like identifying this side with this side in the same exact orientation. So I'll put an arrow here to indicate that this is going up, and I glue it in the same direction so that the arrows are pointing the same way. If I do that, I just get a cylinder, which is what we drew originally, which is going to have an inside and an outside, no problem. What happens though if we reverse the orientation on this? When we glue these together, we still want the arrows to be the same. So in order to do that, we'd have to twist first and then touch it over there. So you'd end up getting a strip that kind of looked something like this. So if I take this strip here and I twist it, now this arrow is going to be pointing up, and then I rotate it in. And so I end up getting something that looks a little more like this, where you have a twist there. And this ends up being the Mobius band. It doesn't have, it only has one side, because as you go around this edge here, you end up rotating in, going through the inside, and then rotating back out and going out the outside. So it ends up only having one side. And that's how you create a Mobius band, is you take a cylinder and you just glue the sides in opposite direction. Well, it turns out that the Klein bottle has a similar relationship with what's called a torus. If I glue those together that way, and I glue the top to the bottom here, this will roll up and then roll up again. So you can see this from an animation that I made for another video. About a month or so ago, I posted a video about how classic JRPG world maps were actually toruses and did this precise thing. So you can see how this is a torus here. Well, what if we just did the same thing and we just put a twist in it? So we'll realign it so that it does that, so that in order to get these guys to line up so the arrows are pointing the way, I'd have to have a twist. So I end up getting something that looks like this again, right? Only this time, this edge here is still aligned, still glued with that one there. And so it still rolls up. And that's where we got that sort of weird looking shape where you get this Klein bottle that comes in on itself. It self-intersects inside, and then there's a hole in the bottom here. And that's the idea of basically rolling first up the top and the bottom here into a cylinder. So here's where they glued together. So that's your arrow there. This arrow, when I roll that forward, is going down back here and up in the front. So it's rotating that way because I rolled this up towards the front, towards the video camera. When this one rolls up, the back part is going up and this part's going down. So you can see that if I tried to roll it up and glue it together, this guy here would try to match with this guy here, the two front arrows, and they'd be pointing opposite directions. And the back arrow here would roll up and try to match with the back arrow there, and they're pointing in opposite directions. So in order to get it to work, you have to roll it up, but then take this side and push it in so that the front end here ends up touching the back end there, and the back end here ends up touching the front end here, so they're in the right order. And that's what this depicts, is a roll up, and then it comes in, and what was the front end here is now touching the back, and what was the back end here is now touching the front. So that's the reason why it ends up looking sort of like that. So that's how you make a Klein bottle. So the next fact that we brought up was the idea of Fermat's last theorem. Now, in order to really understand Fermat's last theorem, you have to actually read Andrew Wiles' proof, which is just, it's beyond, like, I've never read it. It's complicated. It is really, really hard. It's some deep number theory and some elliptic curve stuff. It's not really something I've ever studied before. And so I don't know the details exactly about how Andrew Wiles proved it. If you're interested, please go read his paper. It's some fascinating stuff, and there's a whole rich number theory universe out there to understand. It's not my specialty. I'm a differential geometer by trade, and so it's not really something that I know a ton about. So instead of showing you why it's true, because it's kind of complicated and outside the realm of my expertise, instead I'll show you kind of a fun little issue that Star Trek had with this. In the second season of Star Trek: The Next Generation, there's an episode called The Royale. Now, the episode itself is not actually what's interesting here. What's interesting is what happens in the cold open. So they find this planet or whatever, and Riker is on the bridge, and he has to go report to the captain. And so he goes to the ready room, and in the captain's ready room, the captain pulls the screen around and shows him something called
Fermat's last theorem. You're familiar with it?
Vaguely. I spent too many math classes daydreaming about being on a starship.
When Pierre de Fermat died, they found this equation scrawled in the margin of his notes. X to the nth plus y to the nth equals z to the nth, where n is greater than 2, which he said had no solution in whole numbers. But he also added this phrase, remarkable proof.
So first off, Picard's explanation of history of where this theorem came from is mostly accurate. It was in the margins, not of his notes, I guess, but in the margins of a book that he had called Arithmetica, which is kind of cool. But basically the premise of what he said is right.
Yeah, that's starting to come back to me. There was no proof included.
And for 800 years, people have been trying to solve it.
Including you.
I find it stimulating. Also, it puts things in perspective. In our arrogance, we feel we are so advanced. And yet, we cannot unravel a simple knot tied by a part-time French mathematician, working alone without a computer.
What's interesting is that Picard says that in the period of time in which the show takes place, now The Next Generation is set in the late 24th century, so about 400 years after the show aired, he says that no one's ever proven this. It's still a result that we don't know how to prove 800 years after Fermat wrote it down, and we have all this technology. The funny thing about this is that this episode of Star Trek aired in March of 1989, which, as we know from the video that I posted about Math Facts, Andrew Wiles proved Fermat's last theorem true in 1995, about 6 years after this episode aired in real life. So Star Trek was left with this sort of weird commentary in an episode that's supposed to be set 400 years in the future, but aired in 1989, claiming that this theorem, that it hadn't been proved by the time of the airing of that episode, that it was still not proven 400 years later, and here they are with egg on their face 6 years after making that statement. We have a proof of that theorem. So what's a Star Trek creator to do other than retcon the episode? And so there's an episode of Star Trek Deep Space Nine in the 3rd season of that show called Facets. So in this episode, Lieutenant Dax, who's a joined Trill, so she's got a symbiote inside of her that has been joined to multiple different hosts over the last like 300 years or so, she allows the personalities of her previous hosts through some kind of Trill ritual to inhabit the bodies of the other characters in the show. And it gives Dax sort of an opportunity to get to know her other hosts in another way. Well, she ends up having this conversation with one of her previous hosts that's in Chief O'Brien, and the guy's name is Tobin Dax. And she mentions that Tobin, who's very shy and stuff, which is kind of funny because I think he's supposed to be a mathematician, and I guess mathematicians are supposed to be sort of socially inept, I guess. I don't know. I mean, here I am talking to a camera. So anyway, she mentions in order to try to connect with him.
I've been working on finishing your proof of Fermat's last theorem.
You have?
It's the most original approach to the proof since Wiles over 300 years ago.
Thanks.
It's really cool that Dax actually mentions Wiles in that episode. What's interesting about this is that this episode of Facets aired in June of 1995. Andrew Wiles, though first announcing his proof in 1993, it was found that his original proof had a minor hole in it that he worked really hard over the next year to finally resolve, and that completed the proof in late 1994. But his paper of that proof was not published until May of 1995, and this episode aired 1 month after that, citing Wiles' proof of Fermat's last theorem. Great job to the Star Trek creators to retcon something in order to correct something in pop culture at the time. At this point, it doesn't make sense in continuity what Riker and Picard were even talking about, but it's kind of a cool little intersection of real life interacting with the Star Trek series. The next idea I mentioned is the idea of being able to solve a polynomial equation with a general formula. And I mentioned that in the video that we know how to solve, and it's actually not even that hard to derive. You can complete the square to show that to solve any quadratic equation, you can get a relatively simple quadratic formula, which I also mentioned that if that video, the math facts that sound fake but actually sure, gets 1,000 likes, I'll record myself singing the quadratic formula to the tune of Pop Goes the Weasel. So if you want to go see me do that, you should go back and watch that other video and hit the like button. And if you haven't already, subscribe to Scholar Sauce here as well, and like this video too. It helped me out. But anyway, it is true that we can find similar formulas for a general cubic equation and a general quartic equation, but it turns out that you can prove that there are quintic equations for which no such formula could ever be used. And indeed, there are actually quintic polynomials and degrees higher than quintic polynomials that have zeros that cannot be represented with square root or other kinds of radical symbols. How Ruffini and Abel actually proved this is kind of complicated. Galois Theory, which Everest Galois developed before his death, gives a better foundation to try to explain why you're able to prove these kinds of things, and indeed actually shows that with every single polynomial, there is something called the Galois group, and if the Galois group that's associated with that polynomial has a certain property, which is called solvability, I mean, three guesses where they got that term from. If the Galois group associated with the polynomial is solvable, then it turns out that the polynomial itself is solvable by radicals. But instead of going through the details of how to explain that, I thought I might just explain the jokes that I put on their fake gravestones there. So in group theory, you talk about a set of numbers or objects that have an operation on them. And that operation has some properties, which names you're probably familiar with, things like the associative property, identities, inverses. Well, one of the properties that it's not assumed to have is commutativity of that operation. So you could have a group with multiplication or something like that. Maybe it's not commutative. For example, square matrices have a multiplication defined on them that is not commutative. Well, if a group has a commutative operation, then it's referred to as an abelian group. That abelian word is named after Abel. So on his gravestone, I say that no group ever commuted to work without him. I'm talking about that all groups that are commutative are abelian groups, and it's just a fun little pun on his name. The one on Galois' tombstone is probably a little bit more obvious. Galois theory shows that when a group is solvable, then the corresponding polynomial is also solvable by radicals. And of course, he also was incredibly politically active and was considered a bit of a political radical himself. And so his tombstone kind of makes a play on those words and says that he looked for radical solutions in both his politics and his groups. All right, the last two facts that we mentioned have to do with what's called the birthday problem, which is the idea that if you walk into a room, how many people in there does it take before there's a more than 50% chance that two of them have the same birthday? Or what are the probabilities that two of them will have the same birthday? Well, this is a little tricky because you're not saying what's the likelihood that somebody has the same birthday as me. You're saying if I'm in a room with a bunch of people, what's the likelihood that any pair of people in the room have the same birthday? And you can actually figure this out in kind of an interesting way. So let's say that we have two people in the room. We'll use this number k here to indicate how many people are in the room here. And let's, instead of thinking about what's the likelihood that they have the same birthday, which is just 1 over 365, let's instead, it turns out to be easier to explain this if you think about what's the likelihood that they don't have the same birthday. So with two people in a room, the likelihood that the two of them do not have the same birthday is 364 out of 365. And there's 365 days in the year. This just means that the other guy, whatever the first guy's birthday is, the other guy has 364 possible ways to not have that birthday. And we won't worry about leap years. Well, if there's a third person who walks in the room, the only way that the three of them can have no birthday together is if the first two people in the room don't have a birthday, which we know happens 364 out of 365 fifths of the time. So out of that, how many of those produce the third person not having a birthday? Well, of that, the third person's likelihood to not have a birthday that's either of the first two people's, well, there's 363 more days that he could do. And so of this portion here, there's just another 363 out of 365 ways that he could fail to have the same birthday as those two. And you can follow this along. If you do k equals 4, you can kind of see the pattern now. Well, for convenience, we want to get sort of a pattern to this. So here, I'm actually going to rewrite this just a little bit differently. I'm going to rewrite it as 365 times 364 over 365 squared. And you'll notice here that this square here is now the same value as the k here. And that's the reason why I put that 365 on the top, is I want to be able to identify where my index is. Similarly, down here, I'll put a 365 on the top and multiply the other two numbers. And these are all over 365, this time cubed, because I've got those two plus the extra one that cancels with that guy. So this is like multiplying this guy by 365 over 365 and multiplying this guy by 365 over 365. Doing the same thing down here, I end up with yet another pattern. 365 times 364 times 363 times 362, all over 365 to the fourth power. Well, if you look here at the top, you kind of notice that this looks a little like a factorial. But it stops. It stops at this point here. Well, if I think of this as 365 factorial, I got a whole bunch of extra terms here that I don't want to have. So I could put those on the bottom and they would divide out. So I could rewrite this guy as 365 factorial over 361 factorial times 365 to the fourth power. Well, if you notice, this guy here is 365 minus k, minus the 4. And that kind of tells you what the formula's got to be. If you just have k here, then the formula for the probability that none of them have the same birthday is going to be 365 factorial over 365 minus k, parenthesis factorial, times 364 to the kth power. And sure enough, that works up here too. You have 365 factorial over 365 minus 2, which is 363 factorial, times 365 squared. And you can see that's exactly what you'd get when you divide those two. You get those two guys up there. That works here too. 365 factorial over 365 minus 3, which is 362 factorial, times 365 to the k. And so sure enough, all of these formulas are following precisely this guy down here. This, again, like I said, is the probability that none of them have the same birthday. In order to get the probability that at least two of them do, that would just be when this doesn't happen. Well, to get the probability of when something doesn't happen, when you know the probability of when it does, you just do 1 minus it. So the probability, given k people in a room, that 2 have the same birthday is equal to 1 minus that term there, 365 factorial over 365 minus k factorial times 365 to the k. And if you just plug this in for values of k, you'll see that the probabilities go up. The first time that you get a probability that's more than 50% is once you get to 23 people. If you plug in 41, that's the first time you go over 90% likelihood. And if you plug in 70, you get the 99.9% probability that they have the same birthday. And it's just based off of using basic probability and combinatorics. Well, the card situation is actually very similar to this. Well, if you take a deck of cards that has 52 cards in it, the number of possible different ways that it can be shuffled, as we said in the video, is 52 factorial, which is about equal to 8 times 10 to the 67th power. Well, we also said that the time since the Big Bang was about 4 times 10 to the 17th power seconds ago. If you shuffle a deck of cards k times and you have a total possible orderings of 52 factorial, the idea that two of them are exactly the same, that's exactly the same problem as the birthday issue. So we were just trying to see if two people had the same birthday out of 365 possible birthdays. Here we're trying to see if two decks of cards have the same shuffled order out of 8 times 10 to the 67th shufflings. So just like we did before, the probability after you've shuffled the deck k times that two of those shufflings will be exactly the same will be equal to 1 minus, and then we had before, when we were talking about birthdays, it was 365 factorial because 365 was the number of possible days. Here it's the number of possible shufflings. So it's 8 times 10 to the 67th power factorial divided by 8 times 10 to the 67th power minus k factorial divided by 8 times 10 to the 67th power to the kth power. That's also in the denominator like that. So that would be the probability that two of the cards were exactly the same. So what this ends up being is you end up getting something like 1 minus, and then you have like 8 times 10 to the 67 times 8 times 10 to the 67, we'll put them in parentheses, minus 1 times 8 times 10 to the 67 minus 2, all the way down to 8 times 10 to the 67 minus k minus 1. That's what you have on top. And then on the bottom, you have k of these. Well, there's k of those terms. So you just have an 8 times 10 to the 67th here, and another 8 times 10 to the 67th here, and so on. 8 times 10 to the 67th here, dot, 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 8 times 10 to the 67th. So this is what we get here. And as long as k is not close in size to 8 times 10 to the 67th, all of these things will still be pretty close to just 8 times 10 to the 67th. Like if I subtract 1 off of 8 with 67 zeros, that's still basically that there. So let's suppose that a deck of cards has been shuffled every single second since the Big Bang. In fact, let's do one better. There's 8 billion people on the earth right now. And let's suppose that all 8 billion of those people shuffled a deck of cards one time every second since the Big Bang. Okay, since that many times ago. Well, so 4 times 10 to the 17th times 8 times 10 to the 9th would give us 32 times 10 to the 26th, or about 3 times 10 to the 27th. So if every single person on the earth shuffled the deck of cards every single second since the Big Bang, one time a second, well, shuffled it. I mean like shuffling it 5 times. They're shuffling fast. Okay, if every single person on the earth today was shuffling a deck of cards every single second, since the beginning of time, you'd still only have shuffled that deck of cards 3 times 10 to the 27th power times. Well, that's 40 orders of magnitude smaller than the number of possible ways of shuffling the deck. This k is going to be like 3 times 10 to the 27th under that scenario. That 3 times 10 to the 27th compared to the 8 times 10 to the 67th means nothing. That would be like a guy with $1 million, which is 10 to the 6th, losing 10 to the negative 30 seconds of a penny. Like that's how little that number is compared to that number. It makes absolutely no difference at all. It's entirely negligible. So for all intents and purposes, even if k is that big, this number is still basically 8 times 10 to the 67th power. So for this size here, each of these numbers all the way across are basically 8 times 10 to the 67th. There's no difference in the size. And they're all being divided by an 8 times 10 to the 67th. And there's exactly as many numbers on the bottom as there are on the top. So each of these basically cancel and you get 1. So you end up with 1 times 1 times 1 times 1, k times, and you end up with just 1. Well, then the probability that two of them were the same is 1 minus basically 1. And that means that the probability is practically 0. So yeah, it's practically impossible that any two decks of cards that have been well shuffled have ever been shuffled the same way twice. Kind of nuts. Anyway, I hope you enjoyed this foray into an explanation of why all these different facts were actually true. If you're interested in seeing another video about math facts that sound fake were actually true, please let me know in the comments and we'll make another one and do another explainer. It's kind of fun to see all these different weird things. If you'd like to see the original video of math facts that sound fake but are actually true, you can click here. Or if you'd like to see that video I mentioned about classic JRPG maps being tori, you can click here. Don't forget to like this video and subscribe to Scholar Sauce, and we'll see you next time.